Welcome into Weld.com, everyone. We are in Denton, Texas at ESAB's Center of Excellence, and I'm with Jake LeGrand.
We're going to be taking a tour, having a handful of high school students. We're going to go over some welding and cutting. Let's dive in.
Let's get into it.
All right, is this everybody?
You guys look sick, man. Look, y'all decked out. So we just got done taking a tour of the whole facility. The place is huge, right? You guys got to see a lot of the production side, a lot of the machinist side of the facility. What other things y'all see out there? Stuff for, plasma tips. Yeah, electrodes.
Yeah.
Dude, they make so much stuff in that facility. It's pretty incredible. We're gonna wrap everything up down here in the lab. We've got plenty of welding equipment. We're gonna start with a demo that I think maybe y'all have never touched before, some AC TIG aluminum. Pretty much a crash course on how to do that, along with some plasma cutting by my buddy Jake here. Y'all ready?
Yeah.
Let's do some welding.
Go team.
All right, so right now we're gonna be doing some AC TIG. Anyone ever TIG welded before? Sweet, so we got a couple of us done some TIG welding. What about on aluminum? So you understand the concept then. Why do we weld on AC?
Yeah, it's alternating current.
But why do we weld on AC? But that is good. Yes, it is, in fact, alternating current. So when we're welding on alternating current, we're going between two of those polarities, positive and negative, right? Those are the two polarities that we're going to work with when we're welding. A lot of times when we're TIG welding steel or stainless steel, we're going to be running DC straight or DC negative polarity. So if you know you're running some DC TIG, just make sure your TIG torch is in the negative. You're good to go. However, for alternating current, we've got to go back and forth because aluminum has an oxide layer on it. What is oxide on steel? Anyone know?
Rust.
Rust. Aluminum oxides too, but it doesn't like eat the metal, it actually protects it. And it has a higher melting point than the base metal does itself. So we have to use alternating current, go back and forth between cleaning on the positive side to the penetrating side, which is the negative. Fascinating, isn't it? And that's why we have to use it when we TIG weld aluminum. Not always have to, there are some particular things, but we don't want to get into that rabbit hole. We're gonna look at the machine itself. We know about amperage, right? That's how much beans you got, how much heat you're gonna be putting into it. Obviously, the hotter we get, the higher amperage we get, cold is lower. This knob down here controls my balance. That balance is gonna control whether or not I'm going into the negative side more or more into the positive side, the more time I spend there. Why would I wanna do that? Because of the cleaning and the penetration. If I need more cleaning on the material, I might have more time in the balance, probably towards this direction right here, 90% or so. If I wanna have less of that balance, more penetration, I don't need a lot more cleaning, we're gonna stay lower onto the 60% or so. Here on this Rebel AC/DC EMP205, you have some more bells and whistles here. There is an up and down slope. We're not gonna use that because if you look, I've got a foot pedal on that ground right there. That foot pedal is like the gas pedal in your car, right? If you set it for 100 amps and you stomp on it, you get 100 amps, right? If you're back up about halfway, what do you think you got? 50, right? But the whole point of it is that is your remote that tells the machine when to turn on the gas, when to turn on the arc, and how to control your amperage. When welding aluminum, because of its thermal conductivity, how fast it gets hot, it'll start off welding really slow and cold. But as that material gets really hot really quick, you'll notice you have to pick up travel speed or you'll have to back up on your foot pedal so you don't melt it. And we're gonna see all that later when you guys all get to try it. We can open up this machine, set our pre-flow and post-flow, and then our remote. We're not gonna have to worry too much about the remote settings because of our foot pedal here. But when we get over into this setting here, this is going to be your offset. It's ESAB's way of separating amperage from balance. So if you have 150 amps, you can pick and choose how much amps you spend in the negative side or the positive side. Not to get confused with balance, but amperage. You can separate that on this machine. And you can also set your frequency. A lot of transformer machines, their frequency usually max out somewhere around 60. This will make completely different sounds when we get to welding. And then we can also turn it all the way up to say, somewhere normal is about like 130, but you can see we can get really, really high with this. To simplify, what frequency will do is it changes the arc, all right? If we focus the arc, we get a higher frequency. If we have that 60 hertz, we get a wider arc. So depending on what joint configuration you're doing, whatever thickness you might be doing, you might adjust your frequency to help with that. That's pretty much all the concept when it comes to the machine itself. We're also going to be running some 4043 filler metal on some 6061 aluminum. We're not going to get into base metal and filler metals. Those are already confusing enough, but we have 100% argon. Most of the time when we do TIG welding, we're pretty much going to run 100% argon. However, you can mix helium, you can mix oxygen, you can mix a couple different elements into your gas depending on what you're doing, and that gets into the weeds, especially when you get into automation. I digress. Let's go to the business end and talk about the TIG torch. Now we're going to simplify the TIG torch. This is the torch, right? It comes in A lot of different variations, shapes and sizes depending on who you get it from, where you get. You've seen two-piece TIG rigs, you see water-cooled ones with bigger heads, smaller heads, twist, flex. Anyway, we're going to talk about the basic one. This is a Series 17 TIG torch. Why that really is important for you to know is when you go to buy these things, you need Series 17 parts. There are different series when it comes to a TIG torch head, and that's how you'll know what consumables to buy. So again, this being just our Series 17, even says it right here on the torch itself. There will be some times where you see an F and a V on these torch along with that designation. That means flex and valve. This does not have a valve. Usually there's a little valve on the back where you can turn your gas on and off. We can do this with the machine and our foot pedal. You heard that gas? Right? That foot pedal is going to tell me when to turn that gas on, so I don't need a valve. And the F means flex. That means that neck is flexible. This does not have a flex neck, and if you try to flex it, it will likely break pretty easily, so don't try to flex a non-flex. Now let's get into some of the consumables. We've got a lot of different consumables for TIG welding. I would say the majority of the time, if I'm welding pipe, stainless steel, carbon steel, anything outside of aluminum or magnesium maybe, I'm going to focus on more of these gas lens configurations. You'll just put these on the torch like so with some insulators and these welding cups, and what that gas lens does, it helps diffuse the gas a little bit better for some materials that are a little bit more sensitive to contamination, so argon needs to be a nice steady heavy flow. What we're going to end up using today is the collet body style. The gas doesn't come out of the screen, it comes out of these little holes on the end there. Once the collet body goes in, we're going to be using a ceramic cup. If you've seen Instagram, TikToks, whatever, you've probably seen a lot of different variations of cups. This is pretty much a good one to go to when it comes to aluminum. I like a bigger, wider cup when I do some steel or stainless steel, along with, of course, these gas lenses. Putting this one on, aluminum doesn't have the affinity for argon like carbon steel or stainless steel, so not only are we going to be running less CFH, we just don't need to diffuse it as much. This little guy is called a collet. This is what holds your tungsten electrode in the torch itself. So we just drop that guy in, and that, depending on the electrode we're running, depends on the collet that you're going to use. The back cap here is what holds that collet and tungsten in place. Does anyone know what tungsten is? It's just a metal, right? It's a piece of metal. It has a super duper high melting point. Way more than steel, titanium, carbon steel, way more. We use tungsten to melt other metals. Everyone's got safety glasses and stuff on. I'm gonna do a quick little prep. I like to use a drill or something that spins. I'm gonna try to do it off to the side so we're not gonna spray anyone. I did that tungsten prep in 2 stages. I ground it on the side of the wheel to make it sharp faster, and then I finished it up by making sure all my grinding marks are going towards the tip. Okay, so if we take a good look, don't touch the top there, but you can hold the bottom if you want. It is hot towards the top, so y'all can pass that around. That is the tungsten. Like I said, it's still warm, so y'all be careful. That's the tip that you want for like carbon steel or stainless steel. You want a nice sharp tip. I'm gonna get another one here. These new inverter machines, you could do so many different types of prep for your tungsten, and it really depends on what you're welding, or really preference. Now I'm going to take this piece of tungsten, just as sharp as the other one there, right, and I'm just going to blunt it. So now we've got that tip is now gone. It's just a little blunt end, right? Little flat squared off end. The reason being is whenever we get into that positive side, an AC waveform, it puts more heat into the electrode tip. Sometimes if we have a really sharp tip, it can't handle that positive side of the polarity. So if we need more cleaning and we have to go towards that positive side, we need to maybe blunt that tip up a little bit. And again, this can change with your frequency and joint configuration. And then our last and final way that we can prep this is by putting a ball onto it. We're gonna put this machine on DC TIG. And remember how I said about polarities? We wanna be running a certain polarity when we're welding with steel or stainless steel. What polarity is that? Negative. So now I'm switching it to positive. When you're on positive polarity, you get more heat at this tip and it wants to ball it. It wants to destroy this electrode. But we're going to use the foot pedal and have full control over that balling of the electrode. So we're going to use our hoods now. We've got our argon on. We're going to purposely hurt this electrode. Shove the electrode in with the loosened back cap. You'll set a certain distance on here. However wide your cup is how long that tungsten should stick out. So the bigger cup, more stick out. So I'm easing into that foot pedal and you can see some action happening. It's not really doing anything to the base metal except some etching. We took that blunt end that we just had, and we balled it up. I'm not going to take it out of the torch, but you can see this little ball on the end of the torch, right? This is more like the old school way of prepping your tungsten for aluminum welding. Now you can even go even further than that and ball it up even more. You can put more heat into it and the ball will get a lot bigger. Now we're pretty much set. We know the consumables. We know more about the tungsten and the prep that goes into it. Now we can do the demo on the actual welding itself. Before we get too involved, we're going to talk about the filler metal. We've got some 4043. This is Alcatech. This stuff's pretty nice. It's made in America. We're going to be welding some 6061. Aluminum's pretty crucial as far as what base metal to filler metal that you're going to be going against. So you really need to try to figure out when you go buy it what welds good with it. So you might need 5356 if you're going to be running a spool gun because it's a little bit more durable to push through a liner or a gun. Whereas 4043 welds a little smoother, you might have some better weldability, but there's other tensile strength characteristics that you have to consider. The other thing you want to know is the different joint configuration. Remember I said all those settings that we're going to weld on depends on what these are. These are 4 of the 5 basic weld joints. You have your outside corner, you have your T-joint, we have our lap joint here, and then we have our butt joint. The last one that honestly isn't super common is when they're like this and you got to weld the edge. It's an edge joint. You'll get different types of grooves and weld symbols that you're going to come across in the industry. We're going to start off by welding this outside corner joint. Depending on the joint configuration, you're going to notice some different heat inputs that go into it. On a T-joint, we have 3 different directions for that heat to run. Whereas on a outside corner, we're welding the edge, which is a lot more heat susceptible than say the center of a plate. Of course, the butt welds only got 2 directions, lap joints. Why this matters is because aluminum is very sensitive to heat input. Let's quit talking, let's weld. Which one first? You pick.
T-joint.
T-joint first. So this is the one that's going to soak up the most heat. So we're going to see about how long it's going to take us to get started. We are running 155 amps right now. Now again, I'm going to be welding on this side of the table, so some of y'all may, some if not all of y'all, will need to come around to give this a look. The first thing y'all are going to notice, see this spot on this other piece of plate? That's that oxidation getting busted apart right there. So that's what I'm going to see first. And it's not like a puddle that you're normally used to seeing when it comes to TIG welding or say stick welding. It's a shiny silver puddle that we're kind of looking for. A bright white one. Are you ready? So we're going to start by easing in to this foot pedal. We'll hear that buzz. We're going to try to point at both plates, and now I'm going to be hammering down. I'm all the way down on this foot pedal. I'm going to make like a 1/8 inch step and then fill. I'm still all the way down on the foot pedal. If you can see, I kind of see that puddle opening its mouth like Pac-Man, and then I'm feeding into that puddle. Now I'm starting to back off my foot pedal because I can see that my puddle's starting to get wider. As I get towards the end of the plate, I'm almost all the way back off that foot pedal now. Like, if you look at my amperage, what does my amperage on the machine say? But the machine was set to 155, right? Yeah. I'm having to control my amperage from one side to the other. On a cold piece of material, I can hammer down at the beginning, and then by the time I get to the end, I'm gonna have to back off. Now, what happens when you think on this side of the material? Do you think I'm gonna have to hammer down on it? No, why? It's already, this sucker's cooking, right? Aluminum has a super high thermal expansion. It gets hot really quick. So here on the second side, I'm gonna ease into it and get to the max amperage, but you'll see that I'm gonna be able to do it a lot faster. You'll notice I'm holding my torch like a pencil. I don't have it like this, not for bench welding, like on a table. I hold it a lot more like a pencil. I'm trying to split the difference of my arc between both plates. Gonna ease into it. We never start off full power, but now my travel speed has started to increase right off the jump. Backing up, backing up, backing up, backing up. And I'm filling into that last bit. I'm still dabbing into that crater at the very end so it doesn't wash out on me. So that's your T-joint. Let's move on to say our outside corner. We've got 157 amps on it. I'm not gonna get to the bottom of this foot pedal before I see something that's gonna be too hot. I'm gonna start by welding it fine, and then I'm going to show you what too hot looks like, because too hot on aluminum is pretty obvious and it gets carried away. You get carried away real quick. All right, so that's what I'm going to show you next. While we're at it, I just want to show you all the difference in frequency here. We were at 130 hertz. We're going to go ahead and change that for this outside corner joint to focus that arc a little bit more. So let's go up to like 300. You're going to just straight up hear the difference. Remember, that frequency is the time, the amount of time it's going back and forth between the two, all right? All right, so I'm not all the way down. Now I'm going all the way down. I'm not going to back off. Instead of backing off my heat there, I just let it run all the way. And you can see we messed that right up. What is nice about doing something like that, that bead doesn't look bad. It's pretty smooth. Check out the back side. It's full penetrated. It's all the way through. So it depends on the weld that you're looking for and what the code's going to ask of you. So speaking of full penetration, we're going to use this joint here. All right, there's no prep on it. There's no gap, but we should still be able to melt this puddle and sink it all the way through. I think we'll be good with these settings as well. So with this one, we're really going to want to see this puddle sink. The only other thing, like he said, with always being comfortable, I'm going to try to make sure that I can finish where I want to be able to finish and reach to where I want to start. Always get ready for where you want to end. The other thing, my filler metal hand doesn't move either. I'm pretty much feeding into this, keeping my hand in one spot. All this to try to stay steady. For this weld, I'm looking for that puddle to sink. When it sinks, that's how you know it's going through the back. We're really letting this sucker sink in there. And I stopped welding because I wanted you guys to see something that happens if you don't properly fill in a crater. Who knows what a crater is? It's the end of a weld. The very end of the weld, when you stop, it is the last part that freezes. If it doesn't have enough filler metal, especially with most types of aluminum, if you don't add enough filler metal to your puddle, it'll crack. Cracks are bad. Cracks are like the worst thing in welding that you can get. Watch what happens when I take this and I don't use any filler metal whatsoever. Once that sucker cools, there will be a crack all the way through it. A lot of aluminum needs everything that's in this filler metal right here. These alloys that go in it, same thing with all your other stick welds and your fluxes and all that stuff in it. There's a reason why we have this stuff. You can autogenously weld, which means weld without filler metal, a lot of materials. Aluminum's very picky. And usually if you go to start doing a strength test, you'll see that crack start forming. I'm not seeing it right now. What do you guys think of aluminum? Fascinating, sounds cool. You get to make some pretty sweet ripples and stacked dimes, right? Everyone likes to see those aesthetics. Aluminum's gonna be the best process to really get some solid ripples. Now that we understand this, did you know that in the 1950s through the 1980s or so, they took a TIG welding arc, restricted it in a tight little hole and pushed a bunch of compressed air through it, and they made plasma. So that's what Jake is about to teach you guys over the next station. Is instead of welding metal together, we're gonna cut it off. So we're gonna go take a look with Jake and do some plasma cutting.
Okay, first question. Raise your hand if you've plasma cut. Interesting. Okay. Oxy-fuel? Okay, just curious. Awesome. My name is Jake LeGrand. I own LeGrand Metal Works, and this is all a side hobby for me. So by day, I'm a structural engineer. I do residential design, went to college 4 years, and in that time, I learned how to weld, fabricate, basically furthered my skills in all sorts of blue-collar work. Even if you were, for some reason, to say, I want to quit welding, the welding class for a little bit, go to school, you can come right back into it. It's one of those cool things. So, what we are doing today, plasma cutting. This is the 70 plus, this is the newest machine, 70 amps on this guy, and basically I just want to show you how we get started and then just start blowing some material away. First step, power. So most machines are 220 and some can run on 120. This specific machine also has an adapter. We can do 120 plasma cutting. You're just obviously rated way less on your cut capacity. 2, We want good dry air. In my shop, and I think also in here as well, we're running 100 PSI off the crank. So you're gonna lose a little bit in your hose, but we want good dry air and then constant air. So this specific building's got like a whole air setup with dryers and filters and stuff, but like my personal shop and like potentially one of you guys, most likely you're gonna get an inline filter. So like this one doesn't have it, but threads into the air inlet, and then, you know, it sticks out usually about yay far, and then this just plugs into that. Next thing, consumables. So this specific machine has consumables for 20, 30, 40, 50, and 70. So like this one's a 70 amp. So with 70 amps with that air, this nozzle is designed for 70, not 69, not 68, not 65. Run it at 70. That's what it's designed for. Go ahead and start passing that around. So what you'll see here is on the bottom side is there's these holes that they actually go all the way through this bottom ring. And what's cool is that creates the tornado. It's taking that electric current in the air all up inside of this assembly, and it's just creating that whoosh. It's swirling around and creating the tornado. But so just like a garden hose, when you all of a sudden have a big hose and you put a reducer down and it, you know, you go to a smaller hose, it's forcing that air. That's exactly what all this is doing. We'll go quickly through the actual components. So you saw some of these made in the factory today. You remember this one, but maybe it was a different color? Yeah, it's electrode. This is the black series. It's supposed to be more durable, last 30% longer. When you're looking at your consumables and making sure that they're good, you can see how on this one, these striations are kind of starting to wave a little bit and they're a little gummed up, a little dirty. You want to be checking these things. You want to be checking your electrodes. And then you also want to look at your consumable tips, because copper has a melting temp. I think it's 1300 or 1400 degrees Fahrenheit. A plasma is able to create 20,000 degrees Fahrenheit. So like on this one, we purposely ruined this. And how we did that, we put it right up on edge and we put it basically right on the material. You know, like a drag tip, and we're gonna get that because I know you had a question. Once you get them out of tolerance, your arc can actually curve. So when you're plasma cutting by hand, if you don't have a nice pristine arc coming out of the gun, your tip's most likely bad. This is a built-in component. I basically just look for any marring, any burn marks, just make sure everything's clean, because once something gets dirty, the flow also becomes dirty. It doesn't, you know, it's not doing this, it's doing that. So I'm gonna go ahead and put new consumables in, and we'll do some various stuff. You know, we got some graded material, thick, thin, rusty. One last thing I forgot to cover, travel speed. So luckily at 70 amps, you're pretty much cooking. Like on this thin stuff, I mean, it's gonna be nothing. On this thicker stuff, you're gonna have to, you know, get the ABCs of welding also applies to plasma cutting. I personally like a nice big sheet of steel that doesn't have like any bumps, any scuffs or anything. That way I can freely flow around. Because like a lot of people, you know, they get that elbow in there and you're restricted. You know, you can maybe do like a lot like this, but if you're trying to cut a circle and come all the way around, something's gonna give and you're gonna have to stop and, you know, reset. Whereas, you know, get a little wider stance, and you can hover around the material. So like I said, 70 amps, it's just gonna blow through this like nothing. So as you can see, literally nothing there. That was easy peasy. You got a little dross build up, but nothing you can't just go. With plasma, as long as it can conduct, you can cut it. So you guys weren't with me, but while you guys were doing some learning, I cut cast iron, lead, steel, stainless, aluminum, copper, bronze, basically everything. I shouldn't say everything because there's a lot of other materials out there, but the main ones that you would come in contact with. All that to say, let's get back to cutting. Nope. Did I turn on the right mode? Oh, I changed it. That's why. Okay, perfect example. I accidentally changed the mode back to the plate versus the expanded. So what was happening is as I'm cutting, I have that circuit finished, and then I hit this big void and my machine's like, there's nothing near me. Pilot arc off. So we're gonna turn that back on. Now we'll try that. Very different. Not all plasma cutters have that, so you just have to check out which one that you have. But super, super handy. Who's got a short name?
Mia.
Mia? All right, Mia. What I'm gonna do is I'm gonna cut MIA. With that, you're gonna have a plunge cut. So with plunge cutting, we're gonna use this big plate just because it's easy to look at. So when you do a plunge cut, you don't want to be straight up and down, because what happens is, right when you initiate that arc, it's gonna hit the material and it's gonna come right back up because you're creating a divot. You basically wanna have an angle and you wanna have, is there a soapstone or a marker anywhere? All right, I personally like kind of block letters. Now, one thing to note here on the A, if you cut out the perimeter of the A, is it gonna look like an A fully? Because it's all gonna blow away. So that's one thing to think about when plasma cutting. And just like with CNC, you have to program in breaks and holds. All right, that looks good enough. Make sure you got clamp somewhere nearby. This will probably throw some sparks because, like I said, we're gonna be doing the plunge cutting, but you got your hoods on, you got your PPE, should be fine. All right. Looky there, just like that, plasma cutting. That's your kind of quick dive course into plasma cutting. Just keep with it, and I hope you guys just keep trying things. Keep trying things and push the boundaries. All right, now that everyone's gotten a tour of the facility, we've got a quick demo from Austin and myself about plasma cutting, TIG. Students are gonna be here diving into stick, MIG.
Yeah, there are a ton of machines in this shop here, so we're gonna have a really great time. TIGging, sticking, MIGging, sticking for sure. We're gonna help these kids out, line them out for whatever they wanna learn. As always, guys, thanks for watching. We'll see you on the next weld.